As many of you probably know, there are two kinds of conferences. Those where everybody speaks about the same thing, and those where everybody speaks about a different thing. And this one has a little bit of both, because everybody is supposed to speak about knots, and yet people do speak, as we have seen this morning, about different things, or at least about the same thing seen from a completely different angle. And I'm going to fit into that scheme. I'm a pure mathematician and analyst, and I'm certainly not going to explain to you why people do knot theory. I leave this to Professor Kaufmann. But one of the answers is that knot theory has huge unsolved problems. The classification of all knots, and even recognizing of the unknot. The little curve here is unknotted. You can see that. And there are many programs that show you that a given curve is unknotted, because you can simply observe the isotopy. You have a space of all possible knots of fixed length, and then you put an energy on this space. And some curves have higher energy than others. And you let your curve flow along the gradient flow of the energy. And you can hope that if it is unknotted, then it possibly unknots. Like that one. Wait a second, it unknots, and it convinces you that it's really isotopic to an unknotted round circle. So, this picture was produced by one of the students of my co-author, Heiko from the Mosel, by Tobias Hermes, a few years ago. And we are going to explain some of the analysis behind the knot energies. Not behind that one which was used to produce that particular movie, but behind a very similar one that is kind of appealing to both of us. I will start slowly. Heiko will gather more speed in lectures 3 and 4. And Marta Szumańska, who is sitting somewhere in the room, will try to help you during the tutorials to understand what you missed during the lectures and to show you some little problems. So, some notation first. Gamma, little gamma, in R3 is going always to be a rectifiable curve, closed, possibly non-smooth in the beginning, possibly even having self-intersections, and capital gamma defined on a segment of length L, where L is fixed, going from this segment to gamma. I will be having some fun with that. Is the arc length parametrization. So I assume that gamma prime is 1 almost everywhere. And the energy I will be talking about is defined in a non-local way. It's one of the possible options. So imagine the following situation. This is a point on my curve. X equal to the gamma of some parameter t. The curve is somewhere here. You just see a piece of it, and this is a second point, y equal to gamma of s. This is the direction of gamma prime of t, and this is the tangent line, t x to gamma, a fine tangent line. I'm looking at the radius of this circle. This radius will be denoted by RTP. TP for tangent and point. That's 2 points, X and Y. And you can easily guess what is, or just compute what is the formula for it. You draw 2 extra lines. This is the right angle, and you see that this angle is equal to that one. So the distance of Y to the tangent line to gamma of X divided by the distance from X to Y is equal to X Y minus Y over 2, this little segment here, divided by R. And it gives you a formula for R and my energy will depend on one extra parameter, Q, which is a real number, and the energy of gamma of the whole curve is equal to a double integral over gamma 1 over R Tp of X and Y integrated with respect to the length on gamma. And if you prefer to think to the power Q. And if you prefer to think in terms of parametrizations, then this is the interval over the square, 0L square. And I try to see what was there. Twice the distance from gamma of S to the line which is defined by gamma of t plus the real line times gamma prime of t over gamma of S minus gamma of t square. If I solve that equation for 1 over R and all these to power Q, ds dt, this is the R-Planck's parametrization. If I'm using a different one, then I just would use the derivative there. That's my energy. Why this one? There are many reasons for it. First reason is maybe that Oscar Gonzalez and John Maddox some 18 years ago suggested, not square but cube, sorry. Suggested this energy as one of the possible knot energies preventing self-intersections of curves and other unpleasant phenomena. And this was just a suggestion, and we wanted to do some analysis and see what effects does this energy have. Second, you can start playing with it, supposing that you have possibly a non-smooth curve, just rectifiable, because then gamma prime exists almost everywhere, and this expression makes sense almost everywhere in your parameter space. And third, you can really expect some smoothing. So a simple remark, if you take Q equal to 2, then this energy is scale invariant. So for Q equal to 2, the energy with the parameter 2 of a curve gamma does not really see what is the length of gamma or what is the scale. If you multiply gamma by, if you blow it up by a factor lambda, any lambda positive, then you obtain the same energy. Because, well, if you blow up lambda, then the radius blows up also, the square of the radius blows quadratically with lambda, and the measure compensates for 1 over the square of the radius. Yeah? So this is perfectly clear. Because of that reason, there is one other property. If you try to compute the E2 energy of any polygon, then you obtain infinity, precisely because of the scaling invariance. Why is that so? Try to look at one corner, cut both segments in two, and let this be, this little portion, let this be gamma 1. Then cut again in two, and let this be gamma 2. And so on. So because of the scaling invariance, you have this energy E2 of gamma 1 equal to E2 of gamma 2, and so on. So all those infinitely many pieces have the same positive energy. So it cannot add up to something finite. So this indicates that maybe for bigger exponents, this energy, which is something intermediate, you will have a tutorial on the knot plot, Rob Schorang's software. And in knot plot you can also observe curves that move along the gradient flow of some energy. As far as I know, this is some energy that models electrostatic forces. Points on different portions of curves repel each other. There are other energies. There is the famous rope length energy. What is rope length? Rope length is something like that. You have a piece of rope of fixed thickness and fixed length, like 1 yard approximately or 1 meter, and you ask how many different knots can I tie using this piece of rope, or what is the shortest piece of that rope that I would need to tie a trefoil. This is a hard constraint. The electrostatic energy has the integrand that is singular at many points in your parameter space. And this is something in between. Everybody who is familiar with a tiny little bit of differential geometry should know that the integrand is 1 over r is finite everywhere. It's even bounded. Maybe we'll write that for C2 embedded curves. So, my goal for today will be to sketch the proof of at least one theorem. Let me take this out. Now let me take this out. Theorem 1. If I have a curve of finite energy and I have an exponent bigger than 2, then first of all gamma is simple, has no self-intersections. And second, if you look at the arc length parametrization, then it is everywhere differentiable. And it is even Hölder continuous with an exponent lambda that I will write down in a second. If you look at the difference of gamma prime at S and gamma prime at T, you obtain a constant here, depending on Q, S minus P to the power 1 minus 2 over Q times the energy, and if you can just use the piece of energy that is that corresponds to this arc. So you have the tangents at two places, gamma prime at S and gamma prime at T, and the curve does something elsewhere. Then locally, to know how much the curve can turn, you need to control only the energy of that little piece of curve in between. And I want to really, as Radmila said in the morning, get my hands dirty here, because I'm not going to care about precise constants in public, but I'm going to try to explain the proof. So the proof of this result has, maybe the most difficult thing is to guess what you have to prove. And this I can try to explain afterwards to anybody who would be interested. But the proof has 3 stages. Stage 1 is to understand that the energy determines a certain scale below which the curve fits into narrow tube. And the technical tool that is used to do it is the beta number of an analyst from Yale, Peter Jones. The second part is iteration of a little lemma that you obtain in step 2, and something that I will refer to as a diamond property. And then comes stage 3, a consequence of step 2 already, and maybe I will stop here, we will see how far I will get, is that after step 2 you already know that your gamma prime is in C0, maybe kappa, for some kappa which is between 0 and this lambda. So this exponent lambda is 1 minus 2 over q. And you cannot do any better. And the last step is improve kappa to lambda. And for those of you who are familiar with some PDE, this is like bootstrap. Like elliptic bootstrap, and already have an inequality, and due to nice properties of your equation or maybe your functional, you are able to do things with that inequality which are initially unexpected, and after a certain time they appear natural. Okay. So let me try to fit a little lemma here. Lemma 1 maybe. So how does one go when one wants to show that below a certain scale or in a certain scale determined by the energy, the curve cannot turn too much? Well, you try to think of the configurations which consume too much of energy. Because you have only a finite energy, you can divide your curve into pieces, this piece, that piece, and not all of them can consume a lot of energy. So I have a little technical lemma here, and it runs as follows. There is a certain constant depending on Q, such that whenever I will make a picture in a second, or maybe I will make a picture first. This is point X on my curve. This is a ball of radius X and 2D. And this is a point Y, which is such that X minus Y is equal to D. So it is midway between the center and the boundary of the ball. So these are 2 points of the curve. And now I claim, so in 3D this would be a cube what I'm drawing, that the whole curve must fit into this tube. So, and the cube, this is epsilon D. This is 2D, and you should think of epsilon as being small, and D as also being small, and how small, and what is the relation between epsilon and D. This is something that you learn here. Whenever epsilon to the power 4 plus 2. So epsilon is small, this is positive, so this is small. D is small, 2 is positive, but I have a minus here, D2 minus Q. So this is maybe small. If D is small and Q is bigger than 2, this is large. So there is a certain balance between the two. One tries to make it smaller, the other one tries to make it larger. But altogether they decide that they want to be above the energy multiplied by constant depending on Q. Then gamma intersected with Bx 2D fits into the tube of radius epsilon D around the line xy. Maybe that's the simplest way of writing that. So if you know that your curve is here, and it is here, and that's all the information you have. If those 2 parameters are like that, then the curve must sit all together. It must somehow do different things, but it has to fit here. How we do that? So of course, let me clean the blackboard. Of course, if you start just with 2 points on the curve, then somehow you have to reach that conclusion using, probably that's what you would guess, using only the information on how the curve behaves in the neighborhood of 1 point and of the second point. This is one of the things I like about Germany. You always write on a clean blackboard. Okay. So, look at 3 sets. A of x will be the set of those parameters, say maybe tau, between 0 and L, for which your curve point lies in a very small ball around x. Yeah, epsilon is small. You imagine that epsilon square is much smaller than epsilon. You take this set. What was my notation if I got lost here? G. Okay. G of xy is a set of parameters that depend on x and y. This is the set of those parameters in 0L where, maybe I should say in A of x, it's going to be simpler, where the angle between gamma prime of t and y minus x is really different from 0. Say between epsilon, you can, I guess that 10 would be enough for the proof that I'm going to show, and if it doesn't work you can use something smaller. So you look at the points which are over there, very close to x, and you, a priori, you started with a very irregular curve. So it is just Lipschitz. You don't assume anything more. The tangent might be pointing anywhere you like. But maybe at some places it is pointing really different from this direction. Really different from the direction from x to y. Like that. And the second set, the last set, nxy, is a of x minus gxy. And now I try to estimate, this is an argument by contradiction, so I will try to estimate the energy from above, from below. One more picture as a word of explanation. This is x, this is y. Those are those little balls that have radius epsilon squared d. And somewhere here you have a piece of your curve. Somewhere here too. What I want to show is that if you take one point in this set G of xy, and the second point W in A of y, which is, so Z is somewhere here, W is somewhere over there, and what else do you know? You know that if you start drawing a tangent to your curve, then this angle is at most something like epsilon. At least something like epsilon, sorry. So, I'm not trying to make it precise now, but you know that if W is somewhere here, very close to Y, then this distance is at least something like epsilon times D. Because this is D, the angle is epsilon, this must be at least epsilon D for small angle. So this means, and this is a simple high school geometry, it's not more complicated, then 1 over RTT at the 2 points is at least epsilon over D, because the RTP is this distance divided by the distance of points squared, and the distance of the points is roughly, there is maybe some constant here. I told you that I'm not going to curve over constant. So the energy is bigger than, it's it's a very naive estimate. The measure of one set times the measure of the other one times the lower bound for the integral. And the lower bound for the integral is the power q of this. Up to a constant. And I know one thing. I know nothing about this set, but I know that this set cannot be too short. Because this is the set of the parameters for which the curve stays inside the ball. And this is the arc length parametrization. So in order to enter the ball, go to the center, and then leave the ball, you need twice the radius, or more, if the curve twists. So this is, again, with some constant, the radius, and you have epsilon to the q, d, to the minus q. So, if we had the measure of this set also comparable to epsilon squared times d from that side, then we would have the energy of the curve bigger than, let me count the epsilons, 2 here, and q, epsilon 4 plus q, times d, 1, 2, minus q, with a constant. But this is a contradiction. So, this set cannot be large. It must be small. If this one is small, then this one has to be large, because together they give you A. So it means that the measure of this nxy, where the tangent is pointing almost precisely directly towards y, is big. This must be epsilon squared d. So this is your first observation. And now, you do a second observation. Maybe I try to squeeze it here. Now you imagine your cube of radius epsilon d around the line from x to y. This is x, this is y. And you imagine that you have a third point, z, somewhere here, which violates the lemma. And again, you try to estimate your energy from below. You try to see that this configuration would use too much energy. So this time, you look at those small balls here and here. And now you try to use, there is a piece of curve here, there is some other piece here, and and the second thing that you do is the following. The energy of your curve must be bigger than the integral over nxy. So you take the points on the curve here in the first integral, and in the second integral you take those points which are close to z. 1 over RTP sine and w to the power q. So what do you know? You know that if you are here in this set, then the tangent points almost precisely up to an error like epsilon 10 in the direction of y. So even if you go up to 2d, this distance, the tangent stays well inside the tube. And this little guy is outside the tube. This is at least half of the radius. So this little ball of radius epsilon squared d really is like that on my picture. And you have a similar situation. This distance here is of the magnitude at least epsilon d, and you have the same estimate. So this gives you again measure of one set, measure of the second set, and epsilon over d to the power cube. Again, a contradiction for a good choice of this little constant c0 of cube in the lemma. Yeah? Okay, so what can you do with that? So we are past step 1. Now I want you to understand why this really, because this happens in really all the scales as soon as you have this condition. It looks like cheating at the beginning because, well, you cannot make d too large if you have fixed energy. You have to then to make epsilon very small. But we need to understand what would happen if we started iterating this observation from the lemma. So I'm going to clean the proof. And try to explain you what happens next. Because up to now there is no hint here why I would need q bigger than 2. Iteration of that. And maybe one last remark, think of epsilon as angle. If you look at this tube, and at this angle here, this angle is, if epsilon is small, and this angle is roughly epsilon. So we are now going to we will be trying to see what happens if we shrink the scale and the tubes possibly tilt with the curve. And we will try to see how much they can tilt. So let me solve this. Okay, let me maybe do the following. So I have x minus y equal to d. D is small. I don't care how small at the moment. And I will look at the sequence dn d over 2 to the power n, starting from n equal to 0, and so on. And I will choose epsilon n so that this balance condition, I will call this balance condition, is satisfied with an equality. So I will take epsilon n equal to some C0 of Q 1 over q plus 4. Energy of gamma to the power 1 over q plus 4 dn. I take it to the other side. So I obtain here a power which is equal to q minus 2 over q plus 4. And it is a certain exponent between 0 and 1. It's very small, its q is very close to 2. And now what happens? Okay, my lemma tells me that if epsilon n and dn satisfy this balance condition, then my curve fits into a narrow tube. So now this may be a step bx above bx to the end. I select yn, which are on the boundaries y0 is equal to y. Dn and gamma. So maybe it would be better if I draw dn here. Okay, so this is y. Far away, this is the boundary of dbx to the n. And you know that the curve goes from here to here. And you look at the intermediate balls. So this is bx dn plus 1. And where can the points lie? Well, I have my tube. This is a tube with this axis. Ln is the line from x to yn. And the curve goes from here to here, but staying in the tube. So my point yn plus 1 must be somewhere here on this little patch of the sphere. And the new line Ln plus 1 can be tilted by an angle that I will call phi n. But the thing that I want to note now is the following. That this series of angles phi n from the first one as far away as we can go is so this is something like epsilon dn, epsilon n dn. So this angle, if this angle was epsilon n, then this is maybe a little bit bigger than epsilon n, but not more than by a constant factor, because this is half of the radius. You have to play with sine and tangent and so on. Maybe there is a constant like 4 here, but up to a constant, this is bounded by the sum of epsilon n's. And you have a formula for epsilon n. And this formula tells you that this is some constant depending on Q, energy to a positive power, 1 over Q plus 4. And what is the formula for the sum of the geometric series? Well, every analyst knows that the geometric series, when it converges, is comparable to the first term, up to a constant factor, depending on Q. So, okay. One more observation. This is strong. Still cannot learn that. One note. So you have some number here. This depends on Q. This is some constant that you could compute explicitly. This is your energy. This is this unknown starting distance. I want to make a little note. My note is like that if d to the power q minus 2 times energy of gamma is smaller than some delta 1 depending on q, which is a small but absolute constant. What happens then? Here you have d to the power kappa. So this is like taking this to the power 1 over q plus 4. And then you get also this factor. So if this is small, then a multiplication by that gives you really a small sum of angles. Then sum of these angles phi n is smaller than, say, maybe 1 over 4, if you want to be very specific. So the curve can tilt, those tubes will tilt, but not too much. They will stabilize at a certain limiting position because the geometric series is convergent. Now I maybe put this up, no. This up, and this down. And I claim that this implies at least two corollaries on the behavior of gamma. First of all, it implies Helder continuity of the parametrization. Everywhere Helder continuity. So maybe I will write here a few corollaries of step 2. So maybe I will just draw pictures. Okay. There is a constant C1 depending only on C2. I use C2 depending only on Q, positive, such that if phi, think of angle, 4 plus Q, times D, think distance, 2 minus Q, is at least C2 of Q energy of gamma, then gamma intersected with a ball, center x, radius 2d, is contained in a cone x, y, phi. This is x. The point y is on gamma and on the cone axis. The distance of the 2 points is d. This is the ball x to d. But if the curve is here and here, then it has no particular choice, but it has to stay inside the cone. Cannot penetrate other portions of the ball, because otherwise the energy would be too big. The second corollary is the diamond property. So the diamond property comes from the simple observation that if I have 2 points at a distance d, I can reverse their rows in that conclusion. And I can start imagining a cone with vertex here and the same axis. And this would also apply to my curve. So it has to stay in the intersection of those cones. So my gamma in bx to d and in by to d has to be contained in the cone x, y, phi intersected with the cone y, x, phi. Phi is the angle here, the opening angle. So where can the curve be, and where does the name diamond come from? Well, if you work on that and you start drawing a lot of pictures, then you draw pictures like that. Like that, sorry. Here, y to d bigger. These are 2 balls. These are their centers. This is d, this is d, this is d, the radius is 2d. And here you have those double cones. And you start drawing things that look like a fish with 2 tails, or, well, they look like double cones. And you know that the curve, if it is here and here, then it has to be inside. If this condition is satisfied, but this condition is satisfied if you start like that and you take your phi equal to this, and it is then very small if you start in a small scale. Why does it imply the Hölder continuity of gamma? Well, because gamma prime of t minus gamma prime of s well can the tangent vectors lie? Well, your curve is inside this little cone, so the tangent vector here must be within that cone, because if you approach x along the curve, you stay within the cone. And where is the second tangent vector? if gamma prime of x of s is here? Well, it must be inside that cone. So this is something like 2 pi or whatever. And this is like some constant times the distance to the power kappa times the energy to a positive power. And the distance is gamma of t minus gamma of s, which is certainly smaller than t minus s, because this gamma is the arc length parametrization. So going from here to here, you use this arc length, so the distance must be shorter. So this is t minus s to the power kappa times the energy to the power 1 over q plus 4. Initially, this is satisfied at all the points where the derivative exists, which is a set of full measure, which is dense. And if you have a uniformly continuous function, for example, a Hölder continuous function, you can extend it from a dense set to the closure in a unique way. There is only one extension. This is a simple problem in analysis. And when you think about it, you know that this implies Hölder continuity of gamma prime. And what is important, you obtain this with a constant that is dominated by a positive power of the energy. Which means that if you have a family of curves with equibounded energy, then they are all Hölder continuous with the same constant and with the same Hölder exponent. And it is an important tool to prove that you have energy minimizers in every knot class, and to tell something about the behavior of the sequences of curves of equibounded energy, to tell something about lower semi-continuity of the energy, and to obtain conclusions that are not so obvious, where you just look for a formula for this double integral, but really the tool behind that is this little picture. And I want to keep it, and we will start from that tomorrow.